Hello, my name is Chaewon Park. I am a master's student at Yonsei University. I am specializing in video anomaly detection. It is a great honor to present my research. Video surveillance cameras are everywhere, widely used for public safety. However, the monitoring capacity is not up to the mark, and automatic anomaly detection systems are in high demand to reduce the monitoring burden. However, we have observed some serious challenges while detecting anomalies. First of all, anomalies can be categorized to two branches. One is the unseen appearances, such as a vehicle on a pedestrian road, and the other is irregular motions, such as fighting and robbery. Because the features of these two branches are different in distribution, these have to be learned accurately and separately. Next, many previous methods have used heavy architectures and pre-trained optical flow networks. However, such approach is very likely to increase the computational cost and consequently slows down the detecting speed, which is a crucial factor in anomaly detection. So, to solve the problems, we propose a spatial-temporal patch transformation. This phase is applied to the training data to enforce normal pattern learning in terms of both appearance and motion. This slide outlines the overall process of our method. The network is built on top of a frame-predicting autoencoder. As you can see, it is consisted of 3-layer encoder and a 3-layer decoder with skip connections to supplement the details while upscaling. The input is a stack of 5 successive frames, and the output is a prediction of the 6th frame. During the training phase, the novel spatial-temporal patch transformation takes place. What I like to emphasize is that this transformation is detached during the inference. So let's move on to the transformation module. The spatial-temporal patch transformation is composed of two components, the spatial rotation transform SRT in short, and the temporal mixing transform TMT in short. For each input, a patch cuboid is selected from a random location, and one of the SRT and TMT is applied randomly to generate irregular parts within the normal frames. The SRT is done by rotating each patch in random directions. This transform generates abnormal appearances within the frames and therefore encourages the model to learn the spatially invariant features of normal events. Next, the TMT is shuffling the sequence of the patch cuboid in the temporal axis. By mixing the sequence, irregular motion is generated. Eventually, the model is urged to learn the temporally invariant normal features in order to generate the correct future frame. To validate the performance of our method, we tested our model with 3 popular datasets, the CUHK Avenue, the Shanghai Tech Campus, and the UCSD PET2. Moreover, we adopted the frame-level AUC as the evaluation metric. From Table 1, it can be observed that the accuracy of our model is competitive to all the other methods. And for the detecting speed, our model shows the best performance, running on 195 frames per second, and it is nearly 30% faster than the second fastest one. These figures are some samples of the generated output and the difference maps of the abnormal frame within the test dataset. The first row is the output from the baseline model, which is the generator trained without the proposed patch transformation. And the lower row is from the proposed model. From the results, it is clear that our proposed method shows a stronger distinction compared to that of the baseline. So that's all for now, and if you have any questions or suggestions, feel free to email me. Thank you.